Hi everyone, this is Maverick Hua, the chemistry guru. Now in this video, we want to go through another exercise involving structural elucidation. Alright, so let's take a look at this exercise. I have a compound P with molecular formula C5H9ON, and given all these observations, P exhibits optical isomerism, is neutral, reacts with sodium metal. On reacting P with lithium aluminum hydride, Q, C5H13ON is formed. When Q is refluxed with aqueous acidified potassium manganate, R, C5H11O2N is obtained. Addition of SO, Cl2 to R will produce S, and under suitable conditions, compound S will form T, C5H9ON, which is neutral, along with white films of HCl. Explain and identify the structures of P, Q, R, S, and T. So in total, we have 5 compounds that we want to identify. Of course, in elucidation, what we have to do is be very systematic. Based on the observations in the question, we have to deduce the type of reaction. And from the type of reaction, we can determine what are the functional groups present that are not present. And then sometimes we can even identify the parts of the structure of the compound and identify the entire compound. So we will have to look at each of these 5 observations given, and along the way, we try to deduce the compound. So let us look at the first observation. Now, observation number 1, P exhibits optical isomerism. So optical isomerism in syllabus, we are interested in a chiral carbon. Chiral carbon, it is a saturated carbon bonded to 4 different groups. So we need a chiral carbon or a carbon that is asymmetrical. It is neutral. In syllabus, the functional groups that are not neutral, that means either acidic or alkali. Acids will be carboxylic acids, phenol. Remember alcohol, even though when we compare acidity, alcohols are considered as neutral. So we wouldn't have any acidic functional groups, no acids, no phenol. Of course, when we look at P, because there's only one oxygen in P, P cannot be an acid functional group anyway. Phenol is also not possible because P only has 5 carbons, so it cannot be phenol as well. But based on the functional groups, we can reason this out. Now, if it is neutral, then it is also not basic. In syllabus, the functional group that is alkali will be our amine functional group. So amine functional group will also be eliminated. So based on the molecular formula for P, C5H9ON, I know that the nitrogen, it is not because of amine. I know the oxygen is not because of phenol, cannot be because of acid group. And if it reacts with sodium metal, then it will mean that the OH group, it is present, because based on the functional groups that we have learned, only acid, phenol, and alcohol will give us hydrogen gas with sodium metal. So I know that an OH group is present. So based on all this information given in the first observation, our deduction will be here. Now, given my compound P, C5H9ON, I know that I have a chiral carbon, carbon bonded to 4 different groups. I know that I must have an alcohol functional group present. So what this will mean is the identity of this oxygen, or the functional group that accounts for this oxygen, is accounted for, but I don't know what this nitrogen is, but at least I know that this nitrogen cannot be an amine functional group. Okay, moving on to the second deduction. On reacting P with lithium aluminum hydride, this is obviously a reducing agent, so we know that this is reduction. Compound Q, C5H13ON, it is formed. So what we can do in elucidation questions is to compare the molecular formula between the reactant and product. Then based on the different number of atoms or species present, I can make some reasonable deductions in terms of the type of reaction taking place. So the molecular formula for P, C5H9ON, comparing this with the molecular formula for Q, C5H13ON, the difference is only hydrogen, and I'm adding 4 hydrogen. So we know that addition of hydrogen, it is considered as a reduction. So based on comparing the molecular formula, I can reason out whether this reaction, it is an addition reaction, elimination reaction, is it an oxidation, reduction, hydrolysis, etc. Actually, we can make some reasonable deduction. And interestingly, based on the number of hydrogen added, we can also make some deduction in terms of what functional groups that is present. So you notice we still have this nitrogen that is not accounted for. So what are some functional groups that we have learned in syllabus that contains nitrogen? We have amine, but we have eliminated that because previously we said that amine, it is basic, but P is neutral. Then we have amine functional group, but based on this guy here, oxygen is already an alcohol, so I cannot form an amide based on just one nitrogen. Then the next functional group that we might think of is nitrile. Nitrile C triple bond N, it is neutral and it contains a nitrogen, obviously. Now the reduction of nitrile, interestingly, if you look at this step here, RCN to RCH2NH2, if I reduce this nitrile to a primary amine, just nice, it is adding 4 hydrogen, and I can also use lithium aluminum hydride to do this reduction. So very likely, this reduction from P to Q is involving the reduction of nitrile in P to a primary amine in Q. So my deduction here is a nitrile functional group, most likely it is present in P, primary amine functional group, it is present in Q. And what we can also do is to add both deductions that we have from the second observation and the previous observation, and we try to make some reasonable deduction. What is a possible identity of P? So up to now, we know that P, I have a chiral carbon, I have an alcohol present, so the oxygen is accounted for. I have a nitrile present, and the nitrogen, it is also accounted for. Now, interestingly, for nitrile, what we also know is that the position of this nitrile functional group, it has to be on a terminal carbon. So it also tells us the position of this particular functional group. Of course, based on this information that we have so far, we can't really work out identity of P, because I know that I have an alcohol, but alcohol can be a primary alcohol, secondary alcohol, or even tertiary alcohol. It can be in so many positions with respect to this 5 carbon. So up till now, we still can't make out a reasonable identity of P, but we should keep that in mind. As long as we have enough information, we should try to identify P as soon as possible. Alright, next observation 3. Observation 3, when Q is refluxed with aqueous acidified potassium manganate, obviously this guy, it is a strong oxidizing agent, so it will be an oxidation. RC5H11O2N is obtained. Again, what we do is we compare the molecular formula between Q and R, and I see what is the changes involved. So C5H13ON in Q to C5H11O2N in R. You notice what I'm doing is I'm losing 2 hydrogen and I'm gaining an oxygen. So obviously this is oxidation, loss of hydrogen and gaining oxygen. Both are considered as oxidation, but interestingly, what we can do is I can deduce that this is an oxidation of a primary alcohol. Now, primary alcohol oxidation, you notice I'm losing 2 hydrogen from the carbon and I'm converting this to an acid group, so I'm also gaining an oxygen. So conversion from primary alcohol to acid group, if I compare the molecular formula, I'm losing 2 hydrogen and gaining 1 oxygen. So what this means is, you notice the alcohol functional group in Q, most likely it is a primary alcohol, because the conversion from Q to R, just nice, it corresponds to the oxidation of a primary alcohol, losing 2 hydrogen and gaining 1 oxygen. Now keep in mind, if let's say I have a secondary alcohol, when I oxidize this to a ketone, the change is just loss of 2 hydrogen. There's no gain in oxygen. So based on the difference in molecular formula, I can actually reason out whether this alcohol, it is a primary alcohol or secondary alcohol. So something interesting that we want to keep in mind, something useful that we want to keep in mind. So I know that there's a primary alcohol present in Q. So if a primary alcohol is present in Q, it must also mean that a primary alcohol is also present in P, because conversion from P to Q, it is just a reduction, and the primary alcohol, it is not affected. And an acid functional group, it is present in compound R. Now what we can do now is we can again add on to the deductions that we have so far. So what are the informations that we have? We know that P has a chiral carbon. Now I know that this alcohol, it is a primary alcohol, and interestingly, a primary alcohol, it is also on a terminal carbon. Now this idea, it is important because it tells me the location of that functional group, so it makes it easier for me to deduce what the compound is. So my primary alcohol, it is on a terminal carbon. My nitrile, it is also on a terminal carbon, and I have altogether 5 carbon. Now, even though 5 carbon looks like a lot of carbon, but if I try to draw some chain isomers out of 5 carbon, we actually only have 3 permutations. Of course, this idea becomes realistic. That means I try to work out all the different possible chain isomers involving that particular number of carbon, and I see how many likely structures there are. The less carbons I have, then it is easier for us to just have maybe about 2 or 3 possible chain isomers, and then we work out some possible identity of the compound. But when the number of carbon gets bigger, maybe 6 carbon, 7 carbon, 8 carbon, then it becomes not very realistic for us to try to permutate all the chain isomers and I see which is reasonable. But you notice in this case, if I have 5 carbon, then if I try to deduce the chain isomers for 5 carbon, it will be straight chain 5 carbon. This is n equals to 4. Longest possible carbon chain is 4 carbon, and I have a carbon group or a methyl group on the second position. So this will be a 2-methyl butane. Now this one, it is longest possible carbon chain n equals to 3. So this is a propane, and I have a 2,2-dimethyl propane. This is also a 5 carbon chain. So we have 3 possibilities. So I think it is reasonable. It doesn't take up a lot of time to work out the chain isomers. Now why am I interested in the chain isomers is because I have the functional groups already. I know that the alcohol, it is on the terminal carbon. I know that the nitrile, it is also on the terminal carbon. And I also know that the compound, it has a chiral carbon. So based on these 3 chain isomers, what I can do is I can put in a primary alcohol, I can put in a nitrile, and I see whether I have a chiral carbon. Then in this case, it is possible that I can eliminate some of these chain isomers, and hopefully I'll only end up with one possible answer. So there's a bit of a trial and error involved, but it is a very systematic trial and error. Of course, if the number of chain isomers possible, it is 5 or 6 possibilities, then it becomes not so realistic. But in this case, since I have only 3 possible chain isomers, I think this is reasonable. We can figure that out. So, which is what we are trying to do here, putting in one primary alcohol, putting in the nitrile, and I see whether I have a chiral carbon. Now for n equals to 5, that means this carbon chain, I can put the nitrile on the terminal position, a primary alcohol on the terminal position. You notice there's no chiral carbon. So this guy, it is not possible. We can eliminate this possibility and this chain isomer. Now for the second guy, where you have a 2-methyl butane chain, you notice actually there are 2 ways for me to put the nitrile and my primary alcohol. I can put the nitrile here and the primary alcohol here. I have a chiral carbon because this carbon is attached to a methyl group, a hydrogen. This branch here with the nitrile, this branch here with the primary alcohol. So therefore I have a chiral carbon. So this is very likely to be the answer. But I can also swap the nitrile and the primary alcohol. So it will become something like this. Then this also has a chiral carbon. So in this case, for this exercise, we will have 2 possible answers. These 2 will be the possible answer for structure P. Now, we have one more chain, right, for n equals to 3. For n equals to 3, I can put the nitrile here and the primary alcohol here. You notice again for this chain isomer, n equals to 3, there's no chiral carbon, so this chain isomer will also be eliminated. What this means is I only have 2 possible structures for P, which will be here. So P will be either of these 2 guys, CN, CH2, CH, CH3, CH2OH, or this is a primary alcohol, OH, CH2, CH2, CH, CH3, and a nitrile functional group. Okay, once we have figured P, then we can straight away determine what is Q and what is R, because we have went through the reactions from P to Q to R. From P to Q, it is a reduction. From Q to R, it is an oxidation. So from P to Q, I just need to reduce the nitrile to a primary amine. So Q will be this structure here. If it is the other possibility where the nitrile it is here, then if I reduce this nitrile, then Q will be something like this. So basically converting P to Q, I just need to target the nitrile, convert the Cn to a CH2NH2. Same thing here, if this is the other possibility, I just convert the Cn to a CH2NH2. Now, the next reaction from Q to R, which is an oxidation reaction, I just need to target the primary alcohol. I just target this CH2OH, convert this to a COOH group. Similarly, if this is the other possible structures for Q, then I convert this primary alcohol to this acid functional group. So the structure for R will be something like this. Alright, we have 2 more observations actually. So we will need to deduce and explain the 2 observations. And of course, we still have some compounds to identify. Now the addition of thionyl chloride, SOCl2, to R will produce S. Now I know that there's an acid functional group in R, and carboxylic acids can react with SOCl2 to form acid chlorides, and this is considered a nucleophilic substitution reaction. So I can have a nucleophilic substitution of acid in R to form acid chloride in S. So the deduction is fairly easy. If I already know what R is, then the subsequent deductions becomes more like a confirmation test. It becomes a lot more straightforward. So highly recommended when we do elucidation questions. If you can identify the compound as early as possible, then it is a good idea to identify the compound as early as you can. You notice what we have tried to do previously is for P, even though we have a lot of carbon and we don't really know what the carbon arrangement is like, we took the trouble to try to draw some possible chain isomers, and we do some systematic elimination because we have actually quite a lot of information, right? We know that I have a primary alcohol, which is on a terminal carbon. I have a nitrile, which is also on a terminal carbon. We have a chiral carbon, which actually tells us a lot in terms of the symmetry of the compound. So based on all this information, we can do some trial and error. We can actually identify the compound P. So once we have identified compound P, then the rest of the steps becomes very straightforward. It is just more like a confirmation. So from P to Q to R, it is very straightforward. And moving forward from R onwards, it should also be pretty straightforward. So I know that R will just be these two compounds that we have identified previously. Conversion from R to S will just be converting the acid group to an acid chloride functional group. I just need to substitute this OH group with a Cl. So this will be compound S. This same thing here. If this is the other possible structure for R, I just convert the OH group to a Cl. So this will also be the structure for compound S. Okay, last observation. Observation number 5. Under suitable conditions, S will form T, C5H9ON, which is neutral, along with white fumes of HCl. So if I consider the functional groups in compound S, because S has an acid chloride and it also has an amine functional group. So if I have an acid chloride and I have an amine, under suitable conditions, it can form this compound and it kicks out HCl. So what possible reaction is this? Now acid chloride with amine, it will undergo condensation reaction to form amine. And then condensation reaction usually will require kicking out of a small molecule, right? So between acid chloride and amine, the small molecule that's being eliminated or being kicked out will be HCl. So just nice, everything it is accounted for, and amide is neutral. So we know that this is a condensation reaction between the two functional groups, acid chloride and amine in S, to form amide, which is neutral, in T, and I get HCl as a byproduct. So what we will have to do next is we want to figure out what your compound T looks like. Because some of us might have a little bit of an issue. What we want to convert is, this is a straight chain compound S, and if one part of your compound is reacting with another part of your compound, then basically what we are forming is a cyclic amide. So how do I convert this straight chain compound to a cyclic amide? So some of us might find this a little bit intimidating or a little bit confusing. So what we want to do next is to go through how to figure out the structure for T. Now basically what we can do is we draw out the structure for S, and of course highly recommended is we draw out as many bonds as possible so that it is easier for us to figure out what the product is like, instead of putting everything together and we just write out the condensed structural formula. It becomes a little bit more confusing. So I know that condensation reaction between amine and acid chloride, the nitrogen will actually function as a nucleophile. So I draw the lone pair on nitrogen, and this carbon, because it is delta positive charge, this oxygen, it is a partial minus charge. This nitrogen will act as a nucleophile. You're going to attack this carbon. Then later, there's some rearrangement reaction, but effectively what is happening is you will kick out your Cl. So this Cl is actually eliminated. Then this nitrogen will actually join to this carbon, and subsequently you will also lose a hydrogen. So let me remove one of the hydrogen. So this is the hydrogen that I'm highlighting that is supposedly removed. So later this hydrogen plus this chlorine will give me the white fumes of HCl. Then more or less the product is something like this, but of course it looks a bit messy, right? So what we do is, how do I convert this from this configuration to the actual structure? We start off by numbering the members inside this cyclo compound, because the first thing I need to figure out is how many members are there in the cyclo compound. Is it 5 member, 6 member, 7 member, or so on? So therefore I can draw a pentagon, hexagon, whatever gun that corresponds to the cyclo compound, right? So numbering the members inside the cyclo compound, it is a very useful first step. We can start off with any position actually, but I like to start up with the acid group. So this is position 1. Then let's say this carbon is position 2. Then followed by position 3. Then this carbon is position 4. You notice nitrogen is position 5. Then after nitrogen, you actually loop back to carbon. So therefore, there's only 5 members in this cyclo compound. I know that the cyclostructure, it is actually a pentagon. So I can draw this pentagon here using pencil, and I can label each of these positions, position 1, position 2, position 3, 4, and 5. Then the next thing I do is I transfer each of this group position by position. So position 1 will be my acid group, C double bond O group. So what I can do is I can use pen to write over the pencil mark, right? So this is a C double bond O group. So this will be position 1. Now how about position 2? Position 2, it is a CH bonded to a CH3. So I'll have a CH, and then I draw out my CH3. So this will be position 2. Position 3 will be a CH2. So this will be a CH2. Position 4, it is another CH2. So this is my CH2. Position 5, it will be a nitrogen. Remember, this hydrogen is being eliminated off. So this nitrogen will only have one hydrogen. So position 5, it is a nitrogen with a hydrogen. Then more or less the structure is out. What we will need to do next is we just need to join the rest of the lines together. I join these lines together using pen. Then later I'll just use the eraser. I erase off the pencil mark, and then the structure will be out. Of course, if you don't like to show in this way, you want to show the skeletal formula for cyclo compound, we basically know what this guy looks like, and then I can draw this again to give me a very nice structure for the compound. So remember, what we do is to convert from straight chain to cyclo compound, or vice versa. I think it is useful for us to number the members inside the cyclo compound, and then I decide whether this is a 5-sided, 6-sided, or 7-sided member. Then I can transfer the functional groups position by position. So instead of looking at this guy and I draw this one shot, we should consider what is position 1, transfer it over, what is position 2, transfer it over, what is position 3, transfer it over, and so on. So let us use this as another example to try to illustrate this whole process again. Same thing, I know that this is a condensation reaction. This amine will actually act as a nucleophile. It will use the lone pair to go and attack this acid carbon, which is delta positive charge. And then it will subsequently kick out a Cl minus. So I can highlight the Cl minus that will be eliminated. I will highlight one of the hydrogen that will be eliminated for nitrogen. Then basically this will be the cyclostructure. And again, it makes it a lot easier if I figure this out. How many members are there in the cyclo compound? By numbering the members in the cyclo compound. Acid will be position 1. This is carbon position 2. This is carbon position 3. Carbon position 4. Position 5 is nitrogen. And then this nitrogen will loop back to acid carbon. Then I notice same thing. This is a 5-member compound. This is a pentagon. So same thing, I can draw this pentagon using pencil. Then I transfer the functional groups position by position. Position 1, it is the acid group, C double bond O group. So I use pen to draw this over, C double bond O group. Position 2, it is a CH2. So I just put my CH2 here. Position 3, it is a CH3. So my CH will be here. I need to draw the side branch, CH3. Position 4 is my CH2, right? So CH2 will be here. Finally, position 5, it is the nitrogen with a hydrogen. So I need to draw the N bonded to a hydrogen. Then I use pen to join up all the bonds between all these guys. Of course, when you look at this structure here, it looks a bit messy. But remember, if you were to write this on paper, the pentagon that you drew is all in pencil. You can use the eraser, you erase this off. Then you have a very, very nice structure. The answer will actually be out. Then we have successfully converted your straight chain compound S to a cyclo compound T. So let me show you the structures for T, because these two looks a bit messy, right? Looks a bit ugly. So if I draw these two guys again, my compound T, the final compound that we need to identify in this exercise, will look something like this. These two guys will be my C5H9ON. Alright, so that was the discussion involving this exercise, which is again on structural elucidation. So you notice what we have done is, again, in a very systematic way, based on each of the observations, we try to work out the deductions in terms of the type of reaction, structures present, and as early as possible, it is a good idea to try to identify one of your compounds, because once I've identified your unknown compound, then the subsequent reactions and the subsequent observations will be more like a confirmation rather than a deduction. So it makes it easier for us to answer the rest of the question. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. Thanks for watching.